Pero como yo no tenía un viaje, pero lo que puse dos. Es que somos la pareja del palo, somos. Entonces yo puedo ser cera, entonces podemos ser calientes. Cuatro a 35, o sea, 10 años de razón. Pero no pasaba. ¿Qué le has dado like? No sé si bajaré a Madrid, pero yo no se repita. A veces doy que no a alguien, no lo sabía.
Welcome everyone. My name is Marek. I'm pleased to let's say launch the next DIPC community seminars today. So our speaker is Paola Ferrario, and she will be talking about her mostly ERC research grant. So Paola obtained her PhD 2010 in Valencia. Then she started working on a next project that I think everyone in this room is familiar with. And 2017, she obtained, I think, important distinction, which is ERC research grant, PETALO, which is basically the title of the talk today. So Paola, please. The first one.
Thank you. Thank you very much for the presentation. So I'm happy to be here today, and I'm going to talk to you about this project, which has the principal aim of using a new technology for positron emission tomography, which is one of the ways of doing medical imaging today. So I would like to start with a question which we have been asked often during our years of research, which is, what is our research used for? Maybe in solid state matter is something that it's easier to answer, but in my case, I'm a particle physicist, and it's not that easy to explain why it is useful to study neutrinos, which are particles that basically don't interact with matter at all. So there are different ways to approach this question, and I think that one of the most known ones and interesting ones is medical imaging. In fact, thanks to the properties of particles of going through matter, it is possible to use them to image the interior of our body by detecting them after they pass through matter. So this is something that has been used since the 1895 when the X-rays were discovered. So we are all familiar with radiographies, which are just high energy photons that pass through our body. And we can make images of the anatomy of our body. And since then, we have gone a long path until reaching in the 70s two new techniques, the computed tomography, which is basically a series of X-rays that gives you in different sections of the body a 3D image of the body, and magnetic resonance imaging. Both of these techniques, which we are quite familiar with, gives you an image of the anatomy of our body. But today I want to focus on a different technique that gives you an image of the metabolic activity of the body, which is positron emission tomography, which by its own name, it's evident that uses positrons, so elementary particles. So the principle, it's quite simple. Well, one uses a molecule of glucose modified. This is injected into the body of the patient. It goes to the areas where the metabolic activity is higher. It accumulates there, so one can, in principle, image those areas. It is used in a variety of applications. Maybe the most known one is to detect tumors. In fact, tumoral cells tend to have a higher metabolism. So the areas of the body where a tumor is present appears in the image as bright spots. But not only that, since glucose consumption is related to the neurological activity, it is used for to monitor neurological diseases such as Alzheimer or epilepsy. It is used to monitor cardiovascular diseases because the glucose molecule with the radio tracer goes around the body, carried by the blood. And in principle, one can tailor specific radio tracers to study any metabolic process. Compared to radiography, so computed tomography or resonance imaging, this is a complementary technique. And in fact, it is often used nowadays at the same time. So you have a CT scanner and in the same place, a PET scanner. So the doctor can see both images, one over the other, and has more information about what is happening inside the body. And also, it is used in some cases when some abnormal changes in metabolism happen before anatomic changes happen. So you can detect, for instance, tumors earlier. So the principle of operation is the following. So we have said there is a glucose molecule. One of the atoms is replaced by a radioactive isotope. For instance, fluorine 18 is one of them. The only requirement of this isotope is that it needs to emit positrons. So it needs to decay beta plus. So the positron at some point annihilates with one of the electrons of the body of the patient. And from this annihilation, 2 photons, high energy photons of around 511 keV are emitted in opposite direction. So what one has to do is to surround the patient with a ring made of photon detectors. So if you detect in time coincidence these 2 photons, for instance, in this detector and in this detector, you can draw a line and you know that your photons have been originated in some point of the line. So crossing a lot of these lines, one is able to do an image of the origin of these gamma, so of the area where the metabolism is higher. Usually, these detectors are crystals, scintillators, so they respond to the arrival of the photons with light. So one detects light, and this is the way we draw all these lines of response. One of the figure of merit of a PET scanner, so to say how good is a technology for PET scanners, is the concept of sensitivity, which is basically the number of coincidences of these 2 photons that are detected by the device per unit time and per unit of activity of the source that is injected. Okay, so the higher the sensitivity, the better your PET scanners. There are several factors that contribute to the performance of a PET scanner. One is, of course, the geometry. So the longer your PET scanners, the better, because you detect more coincidences. So it is better a scan of 2 meters instead of 70 centimeters. But of course, this comes to a price, which is basically the cost of the detector. Another thing is the detector efficiency, and it goes with the power of 2 because we have 2 detectors that have to detect 2 gammas in coincidence. And then the kind of material that you use, ideally you want to stop as many gammas as possible. So the material should be very dense, Iz number. And if you have not that dense material, then you have to compensate with the longer thickness in order to stop as many gammas as possible. On top of that, there is another characteristic is present in some of the scanners, which is the ability of detecting the time of these 2 gammas when they arrive to your detectors. If you don't have time information, you just draw your line. But time information is interesting because the difference in time between the 2 gammas is proportional to the displacement of the true emission point of the gammas from the center of the line. In this way, you can determine, in principle, you could determine exactly the point, not just the line, but exactly the point where the 2 gammas are emitted. Of course, it's not as simple. Well, here you can see in the case of a conventional PET without time of flight, you draw a line and then you assign the same probability to any pixel on the line. So to any point on the line, they have the same probability of having emitted the gammas. But if you have this information of the time difference, you can constrain a point on the line. Of course, this is not a point because you have a finite resolution in your time measurements. So this resolution gives you the width of this Gaussian distribution. So you basically can constrain a segment on the line. So why is that important? Because instead of lines, you have smaller segments in the reconstruction process, you have a much lower noise. So your image results with much more contrast. It takes less time to produce the same quality of the image. So this is particularly important when you have a situation where you have low statistics, for instance, of coincidences, or when you want to lower the doses, the radioactive dose. And this is important, for instance, in pediatric oncology. You cannot give a kid the same amount of radioactive material than to an adult. On the market right now, I mean, positron emission tomography has been there for 40 years, so it is commonly used in hospitals. There are several kinds of scanners. This is a brain size scanner, so it gives you more or less the size of the brain. I just took some parameters from a commercial device, which is a sensitivity of around 100 count per second per kilobecquerel, and the time resolution of 214 picoseconds at full width and maximum. Then we have what are called whole body PET, which covers this size of the body. So it's higher, the sensitivity increases because you have a higher coverage. And the time resolution is a bit worse, but not that much. These kind of scanners are already used in hospitals. And then there is this, the last one, the most recent one, which is a total body PET. So you really cover the whole length of a patient. And recently, the first one in the world has been built. And the main advantage of this is that you have a huge increase in sensitivity. You can image the whole body with just one acquisition. So you can do kinematic studies of what happens in two different parts of the body at the same time. And you have better images for the same exposure time, as I mentioned before, with the time of flight. This, the first full total body PET in the world was the Explorer one, which has already taken clinical images in the US. And they claim a sensitivity about 40 times larger than conventional PET, and a time resolution of 430 picoseconds full width and maximum. Okay, on top of sensitivity, there are other parameters that play a role in PET scanners. One is the energy resolution, which means the precision with which we can measure the energy of the photons that arrive in our detector. Why is that important? The photons have a fixed energy, which is around 511 keV. And if you can measure with a high precision this energy, you are able to reject some events that produce noise in your image. Which are these events? They are events when the two gammas, one or both of the two gammas, interact in the body of the patient before reaching your detectors. You can see here, if they don't interact, you have the line of response, which is a correct one. But if one of them interacts, you draw a line of response which doesn't pass from the true point of origin of the gammas. So if you have many of these kind of lines, which are called scatter fraction, your image is blurred, has more noise. All of this comes down to more noise in your image. This is particularly crucial when you have a total body PET, because the longer your PET scanner, the more line of response you accept at higher angles. Higher angles means that they have passed through more patient, more body, more part of the patient. So there is more probability of doing Compton scatter. So this is, if you have a good energy resolution, what happens? That when a photon makes a Compton scatter in the body, it loses some of its energy. So the photon that you detect in your scintillating crystal has a lower energy. So this is an example of a conventional PET scanner. This is the distribution of the energy of the gammas. If you have more resolution, this peak is narrower, and you can reject more Compton scatter in a more efficient way. The current energy resolution And nowadays, of conventional scanners is between 12% and 20% full width al maximum. This is what crystals provide you. Another point that is important to take into account in a scanner, in a PET scanner, is the position resolution. What I mean is that one can just identify the two detectors, the two crystals that have detected the gamma. So you draw a line. If you don't know in which position inside the crystal your gamma has interacted, you just can say, okay, I take maybe, for instance, the central point in the surface of the crystal, and you draw a line. This line doesn't pass through the true position. This is what is called the parallax effect. So if you have a good position resolution, you can reduce parallax effects, and this also gives you a better, lower noise and a better image reconstruction. So just to sum up, we need good time resolution, energy resolution, and position resolution. So the current technology, as I mentioned before, uses crystals. You have to imagine crystals of few centimeters length and few millimeters square of area. These crystals can be are usually coupled in blocks to photosensors, either photomultiplier tubes or silicon photomultipliers, which I will talk later about. So when a photon enters your crystal, it interacts, and scintillation light is produced. So secondary photons, usually in the blue range of wavelength, and they are detected by these photosensors. And so you can detect the energy, the position, if you can, etc. The kind of crystals that are used nowadays are BGO, LYSO, LSO. So they are all crystals made of rare earth. And as I mentioned, most of people now uses silicon PMs, because while in the past PMTs were used. Okay, so what is the idea of PETALO? The idea of PETALO is to using liquid xenon instead of scintillating crystals. Why liquid xenon? So liquid xenon, well, xenon is an element, is an inert gas. So in principle, it is easy to deal with. It's not toxic. This is important. And most of all, it is an excellent scintillator, which means that produces around 68 photons per keV of energy deposited. And it has two responses to ionizing radiation, such as high energy photons, scintillation and ionization. The scintillation happens through excitation of the atom of xenon. When a charged particle enters the xenon atoms are excited. They combine with other xenon atoms, forming excimers, so dimers with excitation, and then they relaxate, emitting a photon of a specific energy, which in the case of xenon is the distribution of the energy of these photons is around 175 nanometers. So we are talking about ultraviolet range. These photons are emitted with a time constant, which follows an exponential. It has two different time constants. One is very fast, 2.2 nanoseconds. The other one is a bit longer, 27. And then there is a third line, is a third constant, which comes from recombination, because if you don't apply an electric field to your system, you have a recombination of the ionization electrons, and it gives you more light at a delayed time. So in the end, you can model your scintillation response with a very fast component and a longer one at around 40 nanoseconds. Why I'm stressing this thing of the very fast component? Because this is important for time resolution. The faster your material scintillates, the lower the fluctuations that you have in the time determination. So xenon it's interesting. It's an interesting material also because of that. Other features that are important for PET scanners, well, it is transparent to its own scintillation light, so you have very good light collections. It doesn't absorb its own scintillation light. It is a continuous medium. This is interesting because when you have very long PET and you made them with crystals, you have to put together many little crystals. and you have to grow crystals one by one, so they can be different, they can have impurities. Instead, if you have a liquid, in principle, you can purify the liquid all the time by passing the liquid through filters, for instance, and you can reach a uniform response everywhere in your scanner, which helps you in the reconstruction. Also, the mechanical complexity is lower if you have a liquid, let's say a container filled with liquid. On the other hand, there are a couple of drawbacks using xenon, which are the fact that the wavelength is shorter, is not in the visible range. So you need photosensors which are dedicated and can detect this wavelength, which are usually more expensive than the current ones. And then that you need to liquefy xenon. In fact, xenon is gas at ambient temperatures and atmospheric pressure. You need to go to minus 110 Celsius degrees to use liquid xenon. This is not a problem. In fact, well, in hospitals, there are in magnetic resonances, the magnets are kept at 4 Kelvin, so it's not a big problem. You just need to do a cryostatic system. This is just a table with a summary of the property of liquid xenon compared to the other crystals that are used nowadays in PET scanners. So using liquid xenon in nuclear medicine is not a new idea. It was the first one having this idea was Lavoie in 1976. And a few attempts have been made in the following decades to implement prototypes with this idea. So there were basically two kinds of approaches. One was using time projection chambers, meaning that they were trying to detect both the scintillation light and the ionization response of liquid xenon. But this approach had a drawback, which high voltages were needed to drift the ionization charge. Also, drift times imply a longer dead time, so you cannot acquire as many coincidences in the same time. On the other hand, there was this attempt by the Waseda group in Japan of using only scintillation light, so you can get rid of the complication of high voltages, but they were using photomultipliers tube, which are big objects like this one. So for instance, the position resolution was very bad, because you cannot have a fine granularity. And finally, there is this project, this attempt is the only one to my knowledge that is still ongoing. So this is the SEMIS project from the Nantes, the Subate group in Nantes. And they use also a time projection chamber with liquid xenon. So they use high electric field, high voltages. And instead of doing time of flight, they exploit the presence of a third gamma and use the Compton information of this gamma to intersect the line of response. And so basically to consolidate the segment I was talking before with this technique. The status, as far as I know, the status of this project is that they were deploying a scanner in a hospital to do the first clinical trials with small animals. So here comes the PETALO idea. So PETALO, the idea of PETALO, of using liquid xenon with a slightly different concept from before, was born in the context of the next experiment by an idea of Juanjo Gómez Cadenas. And in fact, it exploits a lot of hardware and software techniques which are the same as NEXT. In fact, the idea of using xenon, NEXT, as you know, uses gas xenon, and PETALO uses liquid xenon. And the photosensors that we want to use are silicon photomultipliers, which are also used in NEXT to do tracking. Sorry. So we have a very close collaboration with NEXT in terms of hardware, software, also people. Most of the people working in PETALO work also in NEXT. So the idea of PETALO is using liquid xenon, only the scintillation light of xenon, so to avoid all the problems I mentioned before, and silicon photomultipliers to read the scintillation light. These are, for instance, the arrays that we are using in the first prototype. The silicon photomultipliers are solid-state devices which very high gain, so you don't need a complicated complicated amplification step. They have a fast response, which helps you to maintain a good resolution in time. And also have the very nice features of having a very low dark noise at cryogenic temperatures. So you can improve a lot your energy resolution at the temperature of liquid xenon. They can be of different sizes, but in general, they are small. These are 6 by 6 millimeters square. So you can reach a high granularity and have a good resolution in your position. They can be arranged in a variety of arrays. And last but not least, they are compatible with magnetic fields, while PMTs, for instance, are not. So you can use them in the same place as a magnetic resonance scanner, for instance. Of course, you need for them to be sensitive to the vacuum ultraviolet wavelength, but this is done in commercial silicon PMs nowadays, and the technology is improving. So these are the people involved in PETALO. We are 3 institutions involved, the IPC, Istituto de Física Corpuscular, and the Universitat Politecnica de Valencia. And we are physicist researchers, engineer researchers, postdoc engineers, and 2 PhD students, one of which has just defended her PhD, the first PhD of PETALO. So the first step that we did was to try to demonstrate the feasibility and the performance of a full body, total body PET scanner with this technology. We did that with a Monte Carlo simulation of a fully continuous detector. You can see here, it's basically a cylinder, it's hollow, so it has a hole in the middle. And there are silicon PMs all over the external surface, pointing towards the internal part of the cylinder. We used 6 by 6 millimeter silicon PMs, which is a good compromise between not having too many of them, which is complicated, and having a good granularity to determine the position. So this is an image of the simulation. What we did was to simulate 2 high energy photons in opposite direction, the same that it happens in a true scanner. When they reach the ring, which is filled with liquid xenon, the liquid xenon scintillates. The green lines are the scintillating photons that go all over the place, and they are detected by silicon which are on the external surface. So what we do is basically to separate the silicons in 2 groups, one that is related to this interaction and the other group which is related to this interaction. And we plot the energy, the charge that they detect as a function of their position. This is basically the cylinder. So this plot is just the cylinder which is rolled over, so in a plane. This is the coordinate of the axial coordinate of the cylinder, and this is the angular coordinate of the cylinder. So you can see that there are 2 spots. This is a zoom of the 2 spots where the silicon that have detected most charge are the ones that are closer to the real position of the interaction. So basically, what we do is to use kind of barycenter algorithms, weighting the charge detected by each silicon PM to find the position in these 2 coordinates, in Z and in the angular coordinates. For the third coordinate, which is the depth of the interaction, so the radial coordinate, what we do is to exploit the light spread on the silicon PMs. In fact, if the event that happens is closer to the silicon PM, the light spread is smaller. Otherwise, it's larger. It is an almost linear relationship, so it is very good to extract the position in the radial coordinate. So the results that we found for the spatial resolution are 1-2 millimeters full width and maximum of spatial resolution for events that deposit all their energy in one point, which are photoelectric events, which are the ones that gives you a better reconstruction of the line of response. But of course, we also have events where a Compton interaction happens, so you have 2 different interactions of the gamma in xenon. So the response on your silicon PMs is more complicated. and you make a bigger error, so it is this around 8-9 millimeters full width al maximum. We also estimated the energy resolution that we could achieve, and we found an excellent energy resolution of 7% full width al maximum. And finally, the time resolution that we can achieve with this kind of scanner is also very good, 350 seconds full width al maximum. Also, having taken into account all the fluctuations that you have in a real detector. So the sensors have time fluctuations, the electronics, all of this is taken into account. Okay, so this is enough for Monte Carlo simulations. What we also did was to build a first prototype to prove basically two things: the energy resolution and the time resolution. So this is a sketch of the prototype. This is a box, so a cube, aluminum cube of this size, more or less. We put an array of silicon PMs on this side and on this side. And we use a calibration source in the middle. This is a sodium-22 calibration source, which emits a positron. So it gives us exactly the signal that we want, which are two gammas in opposite directions. These are the two gammas, they interact in xenon, and their light is detected by the silicon PMs. There are a few pictures of our setup. So this is the cube I was mentioning. It is CF100 size, is made of aluminum. And the xenon is inside this cube. This cube is cooled down directly with thermal links, which are these ones that now are hanging, but in normal operation, they are connected to the cube. And they connect the cold head of a cryostat, a commercial one, directly to the cube. So the gas enters the cube and gets liquefied by means of these thermal links connected to the cold head. This cube is placed inside this big vessel, which is kept at vacuum. Why vacuum? Just because this way we can keep the minus 110 degrees in an easier way. It is just for thermal isolation. But it is big enough to host also a bigger detector. This is the gas system of the prototype. As I mentioned before, one of the advantages of xenon is that you can continuously purify it. So our xenon is kept inside this system in gas phase. It is circulated all the time by means of this compressor here. And it passes through this filter, which is a hot getter, which removes impurities such as water, nitrogen, or oxygen. What are the problems? That they decrease the scintillation light, basically. So you want the gas to be as pure as possible. And by continuously recirculating it, you can achieve that. So the cube is inside the vacuum vessel. We use a heat exchanger, which basically puts into contact the gas that enters the cube, which is at normal temperature, and the gas that exits the cube, which is already cold. So by this transfer, you can optimize your cooling and using less power. And well, finally, I wanted to mention the recovery tank, which is, well, it is much bigger than that. I just had to put the insert here. This is basically for safety reasons, because if you have an overpressure in your system, we could just let the xenon go in the air. It is not toxic, it's no problem. The problem is that it is expensive, so we don't want to lose it. And it goes automatically, it goes to the tank. So this tank can host all the xenon that we have and more at up to 3 bars of pressure. And finally, this is a cryogenic bottle, which is what we use. This is just for emergency, so we haven't used it so far. But for normal operations, when we want to open the detector to make some changes or whatever, what we do is to recover the gas inside this bottle with liquid nitrogen for difference of pressure, and then we just recover the gas. We close the bottle, and then we can open the detector. So at this point, maybe some of you are wondering what does xenon look like? Because I did, because before liquefying PETALO for the first time, I hadn't seen xenon, because in Next we just put xenon in bottles and in the chamber, but I never saw it. So it looks like that. Okay, it's like water. So it's completely transparent. In fact, The first time we liquefied xenon, it was during the night. We just turned the cryostat on and we kept it in the night. We came back the day after and we didn't see anything because it was filled completely. So I'm not joking. We were not sure if there was xenon there or not. So what we had to do was to take away some of it until we saw the separation line. So this is xenon. And these are the photosensors that we are using that are on the opposite side of the cube. They are from the Hamamatsu company, are UV sensitive, and have an area of 6 by 6 millimeters square. This is on one side, and there is another one exactly the same on the other side. They have a protective window made of quartz, which is highly transparent to the UV light in front of them to protect them. But as you see, well, some of them has already gone away, so it's not really necessary, just for manipulating them. We digitize the signal of the silicon PMs with 2 ASICs from the PETSys company, which are here. They are designed specifically for this kind of applications. They have 2 thresholds, a very low one that gives you the timestamp of the event for time resolution, and the higher one that gives you that allows you to integrate the charge and gives you the energy measurement. And as I said, yeah, they were designed specifically for PET systems. On top of that, we put inside our volume, we put this sort of mask made of Teflon, because we realized that in our cube, a lot of light was lost because it was a very big volume. So in order to enhance light collections and to do an energy and time measurements as intrinsic as possible to assess the intrinsic potential of xenon, or liquid xenon, we built this piece of Teflon. These are holes that are just one hole in front of each silicon PM. In this way, we are kind of using little crystals of xenon. What I mean is very low, very small volumes of xenon inside of each silicon PMs in order to optimize light collections. There is one of these pieces in front of one array and the same one on the other side. And finally, I wanted just to show you where we put the calibration source. So this is a view from below of the detector. This is the aluminum cube. Now there are all the thermal links connected. This is Mylar also to improve the thermal isolation. And in this in this hole that you can see here, we insert a carbon fiber tube, which is this one. And the source is inside the carbon fiber tube. So the source is in the air. It's not in vacuum, nothing. It's here inside, and it is placed exactly in the middle of the system, the geometric center of the system. We can place and remove the source as we want without opening the chamber, without breaking the vacuum. And so finally, this is our first result. We were able to measure the energy resolution. This is very preliminary. We found around 4% full width on maximum energy resolution, which is much better than any other conventional PET scanners. There is a caveat because our simulations give us a slightly worse value of 5.8%. So we are investigating why. A possible problem can be that we are saturating the silicon PMs, meaning that we have too much light and the silicon PMs are not detecting all the light, and an effect could be that your Gaussian is narrower. So we are investigating that. Anyway, even if that is the case and we have this kind of number of energy resolution, this is an excellent result, which could improve greatly the field, because as I said before, the current resolution are around 15% full width on maximum. So just to conclude, well, I presented this new technology for the application of positron emission tomography, which can be especially important for total body PET scanners, so long PET scanners. We have built a first demonstrator, which is operating and taking data. We have measured an excellent energy resolution. The final result is still in progress. And what we want to do now is to measure the time resolution, and in the future steps to build a first ring in order to do the image reconstruction of first of phantoms and small distributions of radioactive sources. And that's it. Thank you very much.
Thank you very much. Excellent talk, Mr. Clear. I mean,
I'm glad.
yeah.
People were worried. I'm not going to understand
I'm
them.
very impressed how you explain all the details. Yeah.
I'm glad that I managed to.
Time for questions.
I'm curious about one thing. You mentioned these 300 picoseconds. That's the time resolution for a single event, or
This is the time resolution that you extract from your system that allows you to constrain a segment on the line of response.
okay. And that's determined by the response of your detectors, or is it the electronic outside?
It depends on a lot of things. One thing is the scintillation time of your scintillating medium. So the faster, the better. Another thing which has actually a very important role is the electronics, because it gives you some fluctuations. Silicon PMs themselves gives you some fluctuation, because a silicon PM is just not a unique sensor. It is made of micro cells. So depending on which cells detect each photons, the time from that it takes to go from the cell to the digitizer is different. So this introduces also a fluctuation. So there are several aspects. Some of them can be reduced, like the electronic. In principle, one can think about improving. There are now attempts to do electronic of 10 picoseconds. At CERN, for instance, they are working on that. So that can be reduced. Other things cannot, that are the physics related things.
Is that a good resolution? So is that sufficient?
So it is very good. Right now, the only full total body pack that exists has a 430. So 350. I wouldn't say that is a chain breakthrough, but is better, or the same order, or better than what is in. Of course, this is a simulation, so we have to prove it. But it's this is motivation.
So I'm wondering, you mentioned that the Suatec group, basically the thing that the characteristic thing is the source that they're using.
Yes, they use a source which has a third gamma.
It's something that you use.
We could also use that, but it is equivalent to have a time of flight. And on top of that, you have to do Compton kinematics. So it is basically another way of constraining a segment on your line instead of. So if you have good time of flight, you don't need Compton. It gives you the same advantage, let's say.
I think I think the liquid xenon right now is quite expensive, right?
Yeah, right now it is very complicated. The situation is complicated because of the geopolitical situation.
Yeah. So what would it be possible to use, for example, argon, and like how much the performances would?
So the problem of argon is that it's much less dense than xenon. So you lose sensitivity there. So either you put more thickness of argon, or you are lost there. And if you put more thickness, you have a worse resolution in terms of everything, reconstruction, energy. So I know that there is a group in Italy which are trying to build a PET based in argon doped with xenon. So
Yes,
they are trying that path. Cristiano Galbiati. Yeah. They are trying that path. From my point of view, it is much more complicated because they are putting 20 centimeters of argon. This is a lot, and it's very complicated. It complicates the design a lot. You have to read. They want to read the light not only at the end of, as we do on the external surface, but inside. So I don't know. But yeah, this is what they are trying to do. This is a simpler design.
So as of today, this would cost more than LISO.
Yeah, today, yeah. Well, the problem is that also LISO and this kind of materials are fluctuating. The market is also fluctuating a lot. It is basically all of them comes from China, as far as I know. So it is also not well, it's not clear what the market does. But yeah, right now, xenon is a mystery. It goes up and down. So as far as I know, there are attempts to try to produce more xenon in Europe, because so far it came from Russia, basically, the xenon. So let's see how it goes.
somehow related to your answer, you have said that if, for example, if you mix with argon or whatever, then you have to put more volume. And which is the optimal volume that you have calculated for your device, for your design?
So we have done some simulations, and the optimal is 3 centimeters, which is basically 1 attenuation length of xenon. In crystals, they use 1.5 centimeters, which is more or less 1 attenuation length of the crystal. So you keep 60-something% of your interactions, which is sufficiently good. If you go to 4 centimeters, you gain a bit on number of interactions, but you lose in terms of reconstruction. So according to simulation, it seems that is one attenuation length of the material.
Is there a way to translate this energy resolution into space resolution?
Yeah, this is the big question, which I have already wondered myself. And the answer, as far as I know, is that it's not that straightforward. Just to say, okay, if I have this better energy resolution, I will have an image resolution. So what you have to do is to do the whole simulation, which is also something I didn't mention, but we are also working on the full image reconstruction with Monte Carlo. You have to go through the whole batch. You have to assume some energy resolution, produce the images, and then you can compare the images and see the contrast and how well you resolve 2 points at a certain distance. But there is not an easy equation to estimate that.
Yeah, I have another question. If I understood properly, you said that you use the spread of the signal to get some information on the radial coordinate.
Yes, right? Exactly.
But so I can understand that statistically there might be a relation, but I don't understand why for a single event.
No, but this is statistically in the end. So it gives you a statistical answer, and if you have millions of these lines of response. So in the end, you use statistics there. Okay. Yeah, no, if you have just one, no, of course. Okay. You have you use like tens of millions of lines to reconstruct one image. Yeah, good point.
Do you see this technology in next years bringing to the market?
So I think that it can totally be to the market if we demonstrate that there is a very good improvement. It's just, I think that it's not enough to have a small increment. It must be a game changer. And so in that case, I think that it would not be a problem. Well, depending on xenon cost. Xenon cost is nowadays is the big problem. But since it's something that can change, I'm not worried about that now. I mean, I'm doing my research. I'm trying to demonstrate the feasibility of the concept. Maybe in 5 years, the situation has changed. What is, I think, the problem is that if in the end it is good, but it's not that good, probably in hospital, doctors don't want to change what they are used to unless there is a very big improvement. So this is my assessment.
So we have no questions from the audience online. Before we finish, just quick announcement. So we have pinchos and in the coffee corner. And if there's no more questions, let thank again our speaker.
Ahora ya puedo.
Esa es buena idea. ¿Verdad? ¿Cómo digo?
Ah, sí, que ya sí.
silicon verde.
170.000 ¿cuánto eso tiene que ir a poner? ¿Cuánto es el costo?
O sea, por la- pero ni siquiera por el mismo.